Okay, it's Thursday, May 20th, 2021, Aerospace Engineering. I'm going to try to teach a little bit about interplanetary travel. Wow, how's that for a topic? So, once upon a time, I passed out a reference sheet, the Aerospace Engineering, Orbital Mechanics, and Astronomy reference sheet. And on this fine document, I see this particular version is incomplete because normally I have a bunch of reference information here, I think. And now the information's here on this handout, but okay. The universal gravitational constant, some data about the sun, the earth, the moon, and Mars, which is pretty much the extent of my interest. A diagram reminding you how to do a Hoffman orbit transfer to change from one circular orbit to another circular orbit, and the slew of equations and terms that go with it. So the ones I want to point out for the moment deal with rocket fuel calculations. When you have a rocket, it has some fuel on board. So those are fuel tanks. It has a payload, which is, and the structure that holds the rest of the rocket. To calculate performance for a rocket, you need to know what kind of fuel you're working with. So for real space travel to get off planet Earth, we need extremely high performance rocket fuel, and a little Estes B motor won't do the job. So we're often looking at liquid hydrogen and liquid oxygen. That's been the go-to choice for extremely high performance rocket engines for decades. SpaceX has been developing methane oxygen rocket engines. Now, these are not as high performing as liquid hydrogen, liquid oxygen. Oh, I'm going to talk about a performance number. So when you have a car going down the road, imagine that's a car going down the road. We can talk about how great the mileage is, right? So we talk and say, oh, I have this little tiny car and it gets 40 miles per gallon. And you say, wow, that's really high mileage. Meanwhile, I have my big truck that I drive and it gets a measly stinking 12 miles per gallon. Okay, so that doesn't tell you how far it goes. It tells you how far it goes for each gallon of gas. So 1 gallon of gas takes this one 40 miles. 1 gallon of gas takes this one only 12 miles. It doesn't tell you anything about the size of their gas tanks. It tells you about how well they use the fuel that you give them. We have a similar measure for the performance of rocket engines, and that performance is called specific impulse. The specific impulse for liquid hydrogen, liquid oxygen is around 450, I'll even say 3 seconds. I think that's what they were able to achieve with the space shuttle main engines, and it took them years and billions of dollars to develop these super high performance engines. And they could be used, I don't know, maybe 3 times before they had to be completely torn down and rebuilt. Something like that. They were high maintenance because they were right at the very edge of what our technology could develop. And this measure here is similar to miles per gallon. It's defined as the number of seconds that 1 pound of fuel can provide 1 pound of thrust. So if I had 1 pound of fuel made out of liquid hydrogen, liquid oxygen as my fuel and oxidizer combination, then it could provide 1 pound of thrust for 453 seconds of time. And that is about the very highest that we can achieve with current chemical propulsion technology. SpaceX has chosen to develop methane oxygen rocket engines, and they're somewhere around 363 seconds of specific impulse. So definitely lower performing by this measure. And of course, the question is, it begs the question, why? Why would they go with lower performing rocket engines? Well, the answer really is because they're looking to the future. You have to understand the motivation for Elon Musk, the CEO of SpaceX, right? So this is NASA, and they spent decades flying the shuttle, and this is what they developed. This is SpaceX, which is a privately owned company created apparently in 2002. Savina read the article by Elon Musk. And it bears worth repeating the story of the creation of SpaceX. Elon Musk was the creator of PayPal, became very wealthy, and wanted to travel into space as a tourist. Well, the only people offering rides back then were the Russians. And it was going to be like $20 million for a seat on a Soyuz spacecraft to go up and do space tourism. When they found out that Elon Musk was really rich, they raised the price and said, "Oh, for you, we have a special price, higher, not lower." And Elon Musk said, "No way, I'm not going to pay more. I'd rather just go build my own rocket." So he went off and started SpaceX here in Torrance, California, and it is thriving as a company. They are really focused, and being focused is what makes all the difference. Hmm. Elon Musk has a vision of creating a transportation system between Earth and Mars. Like the article that just came out describes, written by Robert Zubrin, he wanted to do something that would make him immortal in a sense. And this does happen. Gosh, if you study Bruce Cordell's predictions, this is right smack in the window of opportunity that he had predicted decades ago, where every certain period of time within the United States, there's a opportunity and motivation to do something great. Examples from the past were building the Panama Canal in 1910, landing on the moon in 1969. And by Cordell's calculations and analysis of the factors behind these decisions, right now, this short period of time is when the United States should be aspiring to do something great on a grand scale for future generations. Our country isn't doing that, but as a private person, wealthy enough to do it, we've got Elon Musk and a few other people. It's not just him, but they seem to be taking up the mantle that the nation of the United States is not maintaining. And his vision is to create an affordable transportation system between Earth and Mars. And so this brings us to his choice to use a less powerful rocket engine. The reason, here's his motivation. And it can be explained using the rocket equation. So let me remind you of what the rocket equation says. First of all, we have to calculate how much change in velocity it takes to go anywhere. To get off the Earth, to leave Earth, and just get into low Earth orbit, you need about 9.3 kilometers per second of change in velocity. This will get you into a low Earth orbit. It overcomes the friction in our atmosphere, the gravity turning losses as you ascend. And it's not, exact number. You can tweak it a little bit depending on where you launch from, what your inclination is, and dot 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 dot. But for a good, round number, this is how much change in velocity it takes to leave the surface of the Earth. And where does that get you? That gets you, if this is the Earth, it gets you into LEO, low Earth orbit. Great. Well, what if you want to go away from the Earth? Now that you're orbiting the Earth, to leave the Earth and head off towards the moon or a little bit farther to Mars, the numbers depend on exactly where you're trying to get to and when your target is and where it is. But let's use a round number and say, I don't quite remember what number I should use. I know 3.1 will get you pretty far. Let's go ahead and use 3.1 kilometers per second as the delta V to leave low Earth orbit and maybe even head off to Mars. It might be a little bit higher. I'm still toying with 4.5 kilometers per second, but let's use this. And then what? Let's say that gets you going to Mars. Wow, okay. So Mars is smaller than Earth. It has a very thin atmosphere compared to the Earth. And the engineers say, well, it's too thin to be helpful, like using parachutes, and it's too thick to ignore. So it's just a horrible situation as far as designing how to land on Mars. In fact, there's an upcoming aerospace engineering lecture about the challenges of landing the Perseverance rover on Mars. It's a Zoom lecture. You should attend it, but I haven't shared the details with you. To land on Mars, you can use the atmosphere a little bit to help you slow down. And then you're going to need some sort of additional means to stop yourself. You can't just use the air exclusively as your way of landing on Mars. So I'm going to make up a number. Let's say that you need a change in velocity. I'm going to say around 2.1 kilometers per second to slow down to get to the surface of Mars. These numbers all add up. So if you want to leave the Earth and land on Mars, you need to get off the Earth, leave Earth orbit, land on Mars, and take with you all the fuel. But wait, there's more. Many people would like to go to Earth and return from Mars. Now, not everyone. There are people who for years have said, hey, I am willing to go to Mars on a one-way trip and die there, but preferably in their old age, right? But they would like to actually relocate to Mars. We're ignoring those people for this calculation. We want people who've landed on Mars to be able to leave Mars and go to Earth. Well, they have the physics problem of getting off of the planet Mars. And I believe to get off the surface of Mars. Oh my goodness. We'll pause and you take your 3-minute break. And when you come back, I'll tell you. All right, so during our 3-minute break, I did look up one piece of information that said I had the wrong number to leave low Earth orbit and go to Mars. It's not 3.1 kilometers per second, it's 3.8 kilometers per second. So even more delta V to leave the Earth and go to Mars. While I'm at it, what does it say on good old Wikipedia for landing on Mars, including using aerobraking as part of what you're doing? So I'm going to say it's 0.9 plus 0.2 plus 0.3 plus 0.9 plus 4.1. Well, okay. So landing on Mars, if you're not using aerobraking all the time to do it, it can be as high, so up to 6.4 kilometers per second to land on Mars. Great. So you're on Mars and you want to leave Mars and come back to Earth. That part is going to cost you even more, right? So this is just arriving or arrived at Mars. Okay, so if you want to leave Mars, we're talking about around another 7 kilometers per second, delta V, to get going back to Earth. Now, fortunately, the Earth, as far as we're concerned, has a very thick atmosphere, and we don't bother using rocket engines whenever we come to Earth. We just rely on hitting the atmosphere at just the right angle. And this window is a degree wide, maybe at most. If you hit the atmosphere at too shallow of an angle, you actually skip off the atmosphere and head back off into space. You don't actually land on the Earth. And if you come in at just a little bit too steep of an angle, then you burn up and crash into the Earth. Well, burn up, re-entering into the Earth. So, but we've gotten well enough at this that we haven't incinerated any people yet. And so in this little entry corridor, we hit the atmosphere just right where it slows us down, and we land. Usually in the water because it's so much easier to land in the water than to do a SpaceX type landing on the land. So 0 delta V to land, to return to Earth from Mars if you bring the right hardware to do it. Now, if you wanted to actually just go into low Earth orbit and let's say rendezvous with the International Space Station and be quarantined there, do some scientific analysis there before you try to land on Earth, then you need even more delta V, about the same that it takes to leave the Earth. So on the order of about another 3.8 kilometers per second if you wanted to go to the International Space Station in orbit around the Earth instead of just directly landing on the Earth. So for a round trip from Earth to Mars and back to Earth, we would need 9.3 kilometers per second to leave the Earth, plus another 3.8 kilometers per second to head off to Mars, plus up to, I'm just going to call it 5.3 instead of 2.1 or 6.4. just that's numbers that we've been kind of using. 5.3 kilometers per second to arrive on Mars. Another 7 to leave Mars, usually not even bothering going into orbit first. It depends on which architecture you do, but then head back off to Earth. And so that's a minimum right there of 25.4 kilometers per second. Wow. Wow. What does that mean? Okay, so a round trip, I'm going to just copy it and paste it on the top of this page. Round trip delta V equals 25.4 kilometers per second. And you know that 0.4 isn't really that precise. If I had a rocket engine, these equations dictate how much mass you need to in fuel to deliver so much mass in payload. Okay, so the equation says uh, the final mass is equal to the initial mass that you start off with times E, the irrational number E, 2.7, whatever it is, times raised to the negative delta V power divided by G, really 9.81 meters per second squared is what they tend to use, times the specific impulse also in the denominator. So let's say I start off with a 100,000 kilogram rocket. Okay, so I'm going to just make up a number and say I have a rocket, and this is considered, you know, not a small rocket. It's not a little Estes rocket. So if I start off with a 100,000 kilogram rocket, and I have a delta V of 25,400 meters per second, because we have to work in meters per second. And I'm using G is 9.81 meters per second squared, because they tend to round it up to 1 instead of down to 0 like I usually do. And if I'm using our best performing rocket engines, liquid oxygen, liquid hydrogen, space shuttle main engines, all the way, 453 seconds of specific impulse. How much mass do you think I will have in the end? You know, before we plug it into a calculator, what's your wild guess? If I'm starting with 100,000 kilograms, including the fuel, after this much change in velocity, what's your guess? How many kilograms will I have left in the end? Okay, my students are kind of pessimistic about how much is going to be left over. Let's plug it into the equation. 100,000 kilograms times E to the negative 25,400 over 9.81 times 453. And by the way, the units will all cancel out. The meters cancel, the per second cancels one of these per seconds, and this seconds cancels the other per second. So as always, it's a dimensionless number. We put it into our calculator. 100,000 times E raised to the negative 25,400 divided by, and just to make it clear, I'm going to have open parentheses, 9.81 times 453, close parentheses, get out of the exponent, enter. And it says quit. What have I done? I don't know what I did wrong. It looks fine to me. Drats. I'll type it in again. 100,000 times e to the negative, maybe I use the minus key instead of the exchange key, 25400 divided by, open parentheses, 9.81 times 453, close parentheses, get out of this, enter. Yeah, okay. I should have used the exchange key, and I used the subtraction key by mistake. Okay, so there's the answer. Not much. We end up with 329 kilograms in the end. Now, rockets, to remind you of my excellent drawing of a rocket, is not only the payload in this calculation, but it is also the structure of the rocket. And to leave the surface of the Earth, you need a significant amount of the rocket mass to be the fuel tanks and the engines and the navigation system and, oh man, all this stuff. So typically, for leaving the Earth, somewhere around 11% of the mass of the rocket is not fuel. Or in other words, 89% of the mass of the rocket is the fuel. Okay, so what we have left here is 0.3% of what we started with, right? 329 divided by 100,000 is 0.3%. There is no rocket design that can do that using chemical propulsion, I should say. So why would SpaceX take something that can't even be done and do it with even worse performance? I mean, watch, if the only difference I made was to use the methane oxygen engine instead of hydrogen oxygen engine, this number would become even smaller. Okay? If I used ISP of 363 seconds instead of 453 seconds. Wow. I can just recall the equation and go back and edit the values and replace 453 with 363. Enter. Ah, I end up with a measly stinking 80 kilograms able to do this round trip. And which 80 kilograms is that? Is it the parachute? Right? So making a bigger rocket doesn't solve this problem. If I made this 1,000,000 kilograms, that just moves the decimal place one place here and one place there. It doesn't make it any more viable. So here is the secret as to why Elon Musk, the visionary who's trying to build his immortal vision, is a transportation system between Earth and Mars. And by the way, a round trip transportation system, thank you, is when you look in detail at the planet Mars and that nasty atmosphere it has, there's one thing about it I didn't point out yet. 95% of the Martian atmosphere is carbon dioxide gas. Unlike Earth. Earth, you are supposed to know, is about 79, 78 or so percent nitrogen gas and around 21% oxygen gas, and then trace gases and water vapor and carbon dioxide and argon, everything else. Okay, so what does it matter to us that the composition of the Martian atmosphere is different from the composition of the Earth atmosphere? Hence, the clever concept advocated, promoted by Robert Zubrin starting in 1990 or late 1989. The long story is the President of the United States wanted a plan to send people to Mars. NASA came up with what they call the 90-day study. So for 3 months, NASA put together a PowerPoint presentation on how to send people to Mars. And it said it would take 30 years, cost $500 billion, and put maybe 5 or 6 people on Mars for 2 weeks. Well, a lot of people really choked on that. They said, really? 500 billion years, 30 years for 2 weeks on Mars at the end of all that. And so, out of frustration, the White House National Space Council, directed by Vice President Dan Quayle, said, look, we will listen to any ideas from anybody on how to do this. And even I turned in my ideas. And Buzz Aldrin turned in his ideas. And in fact, he called me up and had me go down to his house so we could discuss each other's ideas and exchange our submissions with each other. And so, wow, for me, that's a big highlight in my life. Shaking hands with Buzz Aldrin twice at his home down in Emerald Bay when he lived there. And he concurred with my ideas, which were, I didn't share with him about this aspect. This is something like submission number 343 to the AIAA outreach program. So if you want to look that up sometime. But Robert Zubrin, then an engineer at Martin Marietta in Colorado, along with Don Baker and someone else, so the 3 guys, they worked out a plan. And their plan worked. And it knocked down the cost of the trip by a factor of 10. That's an order of magnitude. So instead of a $500 billion trip, it only cost $50 billion. And instead of putting people on Mars for just 2 weeks, it would put them on Mars for closer to 2 years, which from a science point of view is great. Wow, we're not just there planting a flag and leaving a few footprints and running back to Earth. We're actually living on Mars for a while and studying it and exploring. This is great. His plan is called Mars Direct, and you're warmly encouraged to look it up. What I can tell you is that Elon Musk, having consulted with Robert Zubrin, has embraced the core concept underlying Mars Direct. And the concept is to exploit the fact that the atmosphere of Mars is mostly carbon dioxide gas. My goodness, what can you do with carbon dioxide gas? Well, you guys took chemistry. You know the carbon dioxide gas is made out of carbon and oxygen, right? Okay, so the concept says if you crack carbon dioxide gas with, I don't know, let's say a small nuclear reactor and some catalyst and stuff, you can break it down into carbon monoxide gas and oxygen. Oh man, we use oxygen to burn rocket fuel. And not to mention humans use it to breathe. So we can convert Martian atmosphere into both rocket fuel oxidizer and breathable air for humans. And let this just go off into the atmosphere if that's what we need to do. But wait, there's more. If only, if only we could find some hydrogen someplace on Mars. Well, back in 1990, it was not very clear that we could find hydrogen lying around on Mars. Of course, here on Earth, hydrogen is everywhere, right? We call it water, H2O. So if you had some hydrogen through the Sabatier process, or whatever it's called, it is possible, and I'm not going to write this chemically correct, but it is possible to create methane. I mean, you got carbon, you got hydrogen, so yeah, methane, and I'm not sure what I forget what the exhaust product is, but I'm going to just say let's pretend that this is the only reaction there is. And then now, if I really wanted to balance it, like in chemistry class, I would try a 2 here. Now I have four hydrogens, one carbon, two oxygens, two oxygens. Why, look, this is a balanced chemical reaction as written. But where do you find hydrogen on Mars? The short answer, the safe answer was you don't. Bring it from Earth. So there's no doubt that you have it on Mars. I mean, after all, when we have a liquid oxygen, liquid hydrogen rocket, there's a hydrogen right there. Just don't use it all up when you go to Mars. The drawback with doing it quite that way is that this is at cryogenic temperatures. So it tends to boil off over time. And it's a 6 to 8 months trip to get to Mars. And then, it's going to take time to convert, to do the chemical reactions to create the rocket fuel. So shipping a tank of hydrogen gas to Mars is not what they suggested. No, 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 no. They suggested that we ship water to Mars, just in case we can't find it wherever we go on Mars. I mean, Mars does look pretty dry. We now know that one of the polar caps is made out of dry carbon dioxide, and the other one is made out of water. But we don't want to be forced to go all the way to a polar cap of Mars to get some hydrogen. So bring this from Earth. And after it gets to Mars, sure, then break it apart into hydrogen and oxygen. This is an unbalanced chemical reaction. A decomposition reaction, you might remember that you're going to need 2 of these and 2 of those for every one of these. Now, here is the beauty of this. You have your own rocket fuel made from mostly the Martian atmosphere. Because when you look at the chemical reactions, you have to look at the mass of these substances, right? What is the mass of hydrogen? One atom of hydrogen is 1 gram per mole. Now, it's a diatomic element, so 1 mole of hydrogen gas is going to be 2 grams. Ooh. What about oxygen? Atomic mass of 16. Carbon, 12. So for the cost of bringing some water with you to Mars, don't drink it. You can exploit the carbon dioxide Martian atmosphere to create rocket fuel and breathable oxygen to use for the trip home. That means the delta V for the round trip to Mars breaks into two pieces. The delta V to go to Mars okay, so one way to Mars. What was that number again? So 9.3 plus 3.8 plus 5.3, I think was what I was using. So 18.4 kilometers per second. And then separately, bring water one way to Earth is 7 kilometers per second. So if we're only going one way to Mars and then using Martian resources for the fuel to come to Earth, what happens to our final mass if we start off with 100,000 kilograms and now our delta V is negative 18,400 meters per second divided by 9.81 meters per second squared times, and here's the reason. Elon Musk is building his engines to run on methane because that is the fuel that is on Mars. That's why. So we're going to use methane, 363 seconds, and calculate. All right, 100,000 times e to the exchange key. And this is, we said 18,400, right? 18,400 divided by, open parentheses, 9.81 times 363, close parentheses, enter. It's better, right? Instead of 329 kilograms, we're up to 570 kilograms. Okay, so that's still only 0.6% of what you started with, right? So it still doesn't work. And so this is where space architecture comes in and builds a couple of additional tricks. So one trick is staging. And another trick, this one really embraced by Elon Musk and SpaceX, is refueling. So staging is where you drop away part of your rocket and you send a smaller rocket up from where this one falls off. That means you're not carrying these huge empty tanks with you everywhere you go. You use a huge engine and huge tanks to get started. And often when we leave the Earth, we use the first stage for about 2 minutes and then dump it and fire up a second stage. Refueling is the plan to go into low Earth orbit and wait there and then bring up a second rocket full of fuel and use it to refuel the upper stage of your spaceship. This might take several trips just from Earth to low Earth orbit. Refuel, and then off you go. So with those two tricks, this number is pushed up to where now we can seriously talk about sending people back and forth between Earth and Mars.